Alrighty, from 19 we move to chapter 20, and chapter 20 really hits the idea of circuits. This very first section, we are dealing with the idea, oops, well that's a big no. There we go. Get that highlighted for me. In this particular section, we are looking at what is a circuit, what basic ideas and definitions are going along with circuits, and how do we represent them. We represent circuits with a schematic diagram. Schematic diagrams just simply show, they say here, the construction of an electrical apparatus. Effectively, they show the pieces and parts that are present with symbols, so don't have to draw the whole thing out. Wires connecting, showing then how things are physically hooked together. So a schematic diagram, the symbols are fairly standard. We looked at some lists of them on your lecture packet. Here we have a picture of a battery and a light bulb. To make that into a schematic, our battery, standard symbol for battery down here, that little guy down in there. And then a light bulb here with wires. There's that wire, and that wire is right there. Very quick, very simple, very easy. Expect that you might have to interpret a schematic diagram or sketch a schematic diagram for the test. If I give you a schematic to either interpret or draw, the symbols will be familiar to you. The resistor, this guy here, battery, switches open and closed, and wires. Don't expect anything that would be different or strange that we haven't looked at. Now, in order to have an electric circuit, basically, that's very standard right there, what we see, a power supply, battery, something that the charges will do work on, a load, in this case a light bulb, a switch that will allow charge to flow or make it stop flowing. If charge flows, we have what is called a closed circuit. In a closed circuit, there's a constant conducting path from one terminal of my battery to the other, from one end of my power supply to the other. So in other words, think about it from practical terms for our purposes. There's always metal for the charges to run through. There's always conductive material for the charges to run through. When, however, that changes, and suddenly there's a place in the circuit where there isn't conductive material present, that's when I have an open circuit. So in this case, if the switch suddenly flipped upwards, I wouldn't have the metal bar of the switch touching the metal pole of the switch. No current. Wire comes loose of the battery. I don't have metal to metal. No current. Filament breaks in the light bulb. No current. So open circuits are off, and closed circuits are on. I said, don't worry about the specifics of the light bulb. That's not exactly a big part of what we're going to be doing on our tests. But short circuits, yes. Short circuits are hazardous. They're a safety hazard. What happens, of course, is somewhere in the circuit, an accidental connection is made that routes around the resistances. I provide a shorter path than the entire circuit itself. I bypass most of the resistance. So for the same potential difference, but resistance drops, usually substantially, it means current rises substantially. And that increase in current can be unsafe. Remember, lots of current means lots of heat production, and that can cause fires. Also, lots of current, that's what electrocutes you. So suddenly we have a situation that may take it from a safe device to one that's life-threatening in a variety of ways. This is where our fuses and circuit breakers came in. Fuse and circuit breaker, if there's a surge in the current, say from you touching a wire or a surge from a transformer, they're designed to open the circuit immediately. No current flows, and whatever that problem is now not going to have an effect on you or any of your electronics. You should know the difference between what we call terminal voltage of a power supply versus the idea of EMF. Very often when we're talking about batteries and generators, we focus in on the idea that they provide the potential difference to allow charges to move through a circuit. That value, a 9-volt battery, a 120-volt outlet, is called terminal voltage. This is the amount of potential energy per charges lose going through the circuit. This is the rating on your battery. However, they also serve, don't forget, as a device that increases the potential energy of the charges in the circuit. In other words, once my charges get back to the battery has to push them back up the energy hill. So if this battery is rated for 1.5 volts, actually this is a 9-volt battery, so we'll say 9 volts. The charge is leaving one terminal, will have 9 joules per coulomb. Returning back to the other, they have 0. My battery would have to fill them back up then to 9, or 9 volts. But the battery itself has internal resistance. So we have to provide from the battery more energy than 9 volts, or 9 joules per coulomb, so that they actually have that terminal voltage when they reach the top of the energy hill. So EMF, okay, is going to be actually greater than terminal voltage, or terminal voltage is less than EMF. If I've got to ensure that you have 9 joules per coulomb, or 9 volts to move through the circuit, I'm going to have to give you more than that as I send you through the battery to account for what's going to be lost by friction while we're moving through the battery. Oh, then we hit this. Resistors in series and parallel. We started by breaking them up. Resistors in series, we have a bunch of loads put in one line or a big loop. One end of the loop connects to one terminal of the battery. Other end of the loop connects to the other terminal. Everybody's aligned in between. Charges run at the same speed between every load, and therefore every resistor in series has the same current. The charges can't pile up in one load and then be absent in the other. They have to move at the same rate through the entire circuit. So very characteristic of series circuits, resistors in the series all have the same current. Now in order to find that current, first thing we do is calculate the equivalent resistance. For a series circuit, we add the value of all the resistors together. My charge down here in figure 20-10 has to go through resistor 1, experiencing all that hardship. Then it has to go through the hardship of resistor 2. The total hardship, the total resistance, would be the sum of both. So in the series circuit, add the resistors to get the total or equivalent resistance. That value will always be larger than the largest resistor in our series, and adding more resistors will put more resistance or make the equivalent resistance larger. For the same battery, that means the voltage is going to go down. So putting too many resistors in a series circuit might take the current down. I apologize. So putting too many resistors in a circuit for the same battery, you might wind up having actually so little current that things just don't work the way that they should. So equivalent resistance, make sure that you can count that. And as I start to look then at potential difference, the idea of what's going on with the voltage with all of my little resistors here, as my charges are moving through at exactly the same rate, i.e. same current, if one resistor is larger than the other, my charge is going to have to use more energy to cross it than the other. They have to move at the same speed. So I use the analogy in class running across, say, your floor versus running through the water in a swimming pool. If I have to run the same speed, I have to put out a lot more energy to try to get to that swimming pool. And that's where the idea of voltage is coming in. So in my little circuit here, just using this guy as an example, the current through each of these resistors is the same. But the size of the voltage of each of these resistors is based on the size of the resistance. More resistance, greater voltage. Smaller resistance, less voltage. And the sum of the potential difference across each resistor better equal that of the battery or be close. We talked about the idea that with rounding it might be a little off. But if you've got a 9-volt battery and you solve for potential differences, add them together, and you've got 13 volts, you've done something wrong. Go back and check. So make sure you can get the equivalent resistance of resistors in a series. That's nice and simple. And then be able to solve for problems such as find equivalent resistance, find the current in the circuit. I would use the equivalent resistance and the battery voltage along with Ohm's law to get the current. And once I have that current, it's the same for every single member of the circuit. Having the current, therefore, for every member of the circuit, I can, with the individual resistances, go back and tell you the potential difference across each one. So we did work this problem. We looked at this problem in class. And of course, you had a whole scat of homework on resistances for things in series. So make sure that you can work those problems and then know all the conceptual things about series resistors. Everything is on or everything is off. A break in a circuit anywhere, the entire circuit is going to go out. Adding more resistors increases the overall resistance, decreases current. Current through each resistor is the same. Potential difference is not the same. It's based on the size of the resistor. So questions could be conceptual. They could also be, of course, solving for what's the equivalent resistance, what's the current in the circuit, what's the potential difference across any resistor. Now, resistors in parallel, I have more than one path for charges to move through. So we see a sample parallel circuit down here. My charges can go through any one of these bulbs, but they're only going to go through one. So whatever potential difference my little charge is carrying, say it's 120 volts, he's going to spend all that energy money across one of these resistors and one alone. So a charge coming through would spend all of his energy money across that light bulb. He'd spend all of it across this one, all of it across that one, and so forth and so on. So in a parallel circuit, all the resistors have exactly the same potential difference. So if this is a 9-volt battery or a 120-volt power supply, it doesn't matter. All of these guys have the same voltage, identical. However, the current, I can't say the same thing. The current's going to be based on the size of the resistor. All my charges, whether they go through R1 or R2, carry the same energy. But if there's less resistance, they can use that energy to run faster, i.e. higher current. Higher resistance for the same energy, they'd run slower, lower current. So the current in my individual resistors will be different, and it will be based upon the size of the resistance. Now, a big thing when we're dealing with the idea of series and parallel circuits is how resistance plays out as I add more and more resistors. In series, adding more and more resistors made for more resistance, less current. It's the opposite for parallel. For parallel, adding more resistors is going to decrease the overall resistance, and it will increase the current. That, of course, can set up a safety situation. If you overload a series circuit, you just don't get enough current for things to run. However, you overload a parallel circuit, you have some severe dangers with too much current in the circuit. That could be heat and a fire or a dangerous current for your own health. So be able to solve for resistors in parallel. What is the equivalent resistance in the circuit? What's the equivalent current? What's the voltage and current across any of the resistors? Now this last bit is really for honors only, and that's the idea of a combined circuit. We've worked some problems with these. This is really a more real-life situation. For honors, there is one of these on your test. So make sure you could take something like this particular figure and solve for the current and potential difference across every single resistor here. We said you start off by working backwards. What's the smallest member of our circuit? Find the resistance, find the resistance, find the resistance. With equivalent resistance of the whole circuit, you can find the current in the whole circuit. And now we can start working resistor through resistor to figure out the information for every single resistor there. I'll do a separate video on how exactly to do these guys, a little refresher. We've done these a few times, but I'll put one more refresher up for people. CP, this is really not your bag, so don't worry about this bit in studying or preparing for your test. So again, we come back to the end of the chapter. Key ideas, read through them. Make sure you're very clear on what information is presented in each section. For formulas, remember, I'm not going to tell you which is which. I'm just going to give you these two. Ohm's law, of course, is the other massive formula in this chapter. The power formulas showed up on a couple of problems. They didn't list them here because they listed them for for chapter 19. Basic symbols, I'd be very familiar with wires, resistors, batteries, switches, open versus closed. Those are the ones I would really pay attention to for your upcoming test. Alrighty, so there's 19 and 20 now, and I'll have a little video up on a combined circuit, and hopefully everyone will do their best with these upcoming tests.